AI doesn't just use a lot of power, it uses it unpredictably, and that second part is actually the harder problem. Most conversations about AI and energy focus on the total amount of electricity data centers consume, and the numbers are genuinely large. The International Energy Agency estimates data centers could account for somewhere around 3 to 4% of global electricity use by the end of this decade. Utilities are already rewriting their long-term forecasts to make room for that growth. That's a real story, but it's not the whole story. The part that often gets missed is what that power draw actually looks like from the grid's perspective. It's not a steady, predictable pull. It spikes, it drops, it surges again, and the grid was never really built for that. Here's why it happens. When a large language model processes a request, it's pushing work through thousands of GPU cores simultaneously. Those chips ramp up almost instantly, pulling huge amounts of power. Then the job finishes. The chips idle. Power drops just as fast. Now multiply that across tens of thousands of chips in a single facility, all responding to unpredictable workloads from millions of users at once. The power signature at the meter looks jagged, not smooth. Grid engineers call this the load variability problem. Grids are designed around something called baseload, the steady floor of electricity demand that doesn't change much hour to hour. Things like factories, hospitals, street lighting. You can plan for baseload. You can build for it. What's harder to plan for is demand that swings sharply in short windows. That's what AI clusters introduce at scale. When demand spikes faster than the grid can respond, voltage can drop, frequency can drift. In the worst cases, protection systems trip and sections of the grid go offline. Grid operators use a concept called inertia to absorb those sudden changes. Traditionally, that inertia comes from the spinning mass of large generators, turbines, rotors, that naturally resist rapid frequency changes. The bigger and heavier the spinning machinery, the more inertia in the system. But as grids shift toward more renewable sources like solar and wind, which use inverters instead of spinning generators, that natural inertia gets thinner. And a thinner inertia buffer means the grid is more sensitive to sudden load changes, which is exactly when large AI clusters are becoming more common. So you have two trends colliding at the same time. Grids are getting more sensitive to load swings, and AI is introducing more load swings. That's the tension. Data center operators and grid engineers are both aware of this, and there are a few approaches already in use or in development. One is on-site energy storage. If a facility has large battery banks, it can absorb a power spike locally rather than pulling it directly from the grid. The batteries charge during low-demand periods and discharge during peaks. That smooths the signal the grid actually sees. Some hyperscale facilities are already doing this, though the battery capacity needed to buffer a serious AI compute cluster is substantial. Another approach is smarter load scheduling. Not every AI job is time-sensitive. Model training runs, for example, can often be scheduled during off-peak hours when the grid has headroom. Some operators are building software systems that shift workloads based on real-time grid signals. The idea is that the facility becomes a kind of flexible demand resource, backing off when the grid is stressed, running hard when there's surplus capacity. This is sometimes called demand response, and utilities have used versions of it for decades with industrial customers. Applying it to AI workloads is a newer challenge because the jobs are complex and the trade-offs aren't always obvious. There's also ongoing work at the chip and server level. Power delivery architecture inside modern AI accelerators has gotten much more sophisticated. Chips now have onboard capacitors and voltage regulators that can buffer rapid current changes at the microsecond scale. That doesn't solve the macro-level grid problem, but it does reduce some of the fastest and sharpest spikes before they ever reach the facility's main power connection. Some researchers and engineers are exploring what they call grid-aware computing. The basic idea is to give AI infrastructure real-time information about grid conditions and let it respond dynamically. If frequency is dropping somewhere in the region, nearby data centers could automatically throttle non-critical workloads for a few seconds or minutes. Done at scale, that kind of coordinated response could actually help stabilize the grid rather than stress it. It turns a potential liability into something closer to a grid asset. That's a meaningful shift in how we think about large compute facilities. Instead of just big consumers of electricity, they could become active participants in grid stability. But that requires tight integration between the software running AI jobs, the facility's power management systems, and the utility's grid monitoring infrastructure. Getting those three layers to talk to each other reliably is a non-trivial engineering challenge. What makes all of this urgent is the pace of deployment. New large-scale AI facilities are coming online faster than most grid infrastructure can be planned, permitted, and built. Transmission lines and substations take years to approve and construct. AI clusters can be stood up in months. That gap creates pressure. Utilities are being asked to serve loads that weren't on their radar 3 years ago, and the load shapes are unlike anything in their historical data. None of this means AI development has to stop or slow down. But it does mean the energy system side of the problem deserves as much engineering attention as the compute side. The chips are getting faster and more efficient. The software is getting smarter. The power infrastructure around it all needs to keep pace, because ultimately, a data center is only as reliable as the grid it's connected to, and the grid is only as stable as the loads it has to manage. Right now, those two things are learning to coexist.